More power.
Mm-hmm.
Electrochemical cells.
Plug into batteries.
Yes, batteries, aka electrochemical cells. Lecture number 6 in our redox unit. Okay. 6. Anyways, we're going to focus on how a battery can work. And this is kind of like the crown jewel of this unit.
It kind of culminates all the little things we learned into one culminating piece.
Oxidation numbers, half reactions, reactivity cell series.
Spontaneous, non-spontaneous.
So a battery is a spontaneous chemical reaction that occurs to create electricity. And we also call them lots of things. We call them batteries.
Yep.
We call them voltaic piles.
Yes.
Okay. All these things are spontaneous reactions that can turn stored up chemical energy into electrical energy. And this is the classic picture of what a battery looks like on the Regents. Okay. There's 2 cups, 2 beakers, this U-shaped salt bridge, these electrodes, and then some kind of wire with a voltaic cell or a voltmeter, or sometimes it's a light bulb even written in the picture.
Yep.
But either way, you have 2 separate reactions connected by a couple different pieces of
That's telling you right off the bat that it's voltaic. You see that voltmeter that helps. The
sometimes.
salt bridge, mandatory.
Definitely.
2 different cups. So all those things we laid out for you are key indicators to let you know it is a voltaic cell you're dealing with.
Or sometimes I've even seen it as 1 cup, but with like a barrier in between, dividing it into 2 different halves.
There is, because there has to be 2 different electrolytes
and 2 different electrodes
to make this whole thing work.
But this lecture is mostly about all the different parts of a working electrolytic cell, voltaic cell, not electrolytic, working voltaic cell, and the chemical reactions that we're going to have to interpret out of it.
Now, conversely, the electrolytic cell is the non-spontaneous reaction that needs the electricity to make it go. We will highlight that cell next video in detail.
It's like when you switch your battery into recharge mode.
So in this picture, we do see electrodes. Those are important. That is the metal that connects the solution to the actual cell. The oxidation number of the metal is always 0. And if you look, you'll see a magnesium electrode solid.
Yep.
And in the equation, it's magnesium solid. That should have a 0.
Yeah, for sure.
Should have a little 0.
Yep.
And same with the copper.
Right. So you got pure elemental metals with oxidation state 0 as your electrodes dipped into solutions
that contain their ions.
So that some transfer of electrons can happen
between common once were atoms.
So an anode is the electrode that's positive, and it's always where oxidation takes place.
Angry ox.
N-ox. Anode, oxidation. And we know oxidation is losing electrons. So we lose electrons into the wire at the anode, the positive electrode.
The cathode is the negative, which will draw them over, right? And then where reduction takes place, red cat. Reduction at the cathode.
And reduction is gaining electrons. So the electrons that travel into the wire on the one side travel through the circuit to the other electrode, where they then team up with the ions. And
the neat part about that is they actually travel right through the electrode and team up with the ions right in the solution.
Exactly.
Which is neat.
So the directional electron flow is really easy, because if you know your alphabet, A always comes before C, and anode comes, the electrons travel from the anode through the wire to the cathode.
That's how you remember it right there. A before C always goes A to C.
There's another way to look at it. It's the more active metal is always the anode. Active anode will lose electrons to the not so active cathode.
Correct. Another good way to look at it. Salt bridge. Now this is key. This completes the circuit. Allowing ions to flow. So that's what you really need to be able to say right off the bat. When you hear salt bridge, what is the purpose of the salt bridge? Very common question. Allow ions to flow. It completes that circuit. So as the electrons come around, if there's nothing going back the other way, it stops and it won't work.
It's a dead circuit.
You need so this is like the physics piece to circuits that we don't do because we haven't taken physics, but it needs to be complete or it won't work. It's got to be cyclic.
If you got a wire cut somewhere in your circuit, the battery is not going to power your device. So you have to have a closed loop for the electrons and ions to travel through.
All experienced that either in the wire to our remote control because we wind it up, or in the wire to our headphones.
One's dead. Oh, I can't hear anything out of this one side. Well, that wire came loose. The circuit is open.
And there is no fixing those things.
There's no fixing those. I mean, you could fix it if you're really good.
All right, so we're going to take this electrolytic cell, and do what we've done in the other practice pages. Okay,
Yep.
so I'm going to take that equation on the bottom. We're
Yep.
going to impose that right up top
Yep.
because this is what we are dealing with our reduction and
Oxidation.
oxidation.
So we're going to track which species lose and gain electrons to decide how many moles of electrons are
All right,
involved.
so let's just
in
think
the
about
half
this real quick.
reactions.
If I go from Mg0 to Mg plus 2, am I gaining electrons or losing?
Oxidation is losing electrons and you become
I
more
did-
positive.
Okay.
So I would say magnesium is becoming magnesium positive 2 and some electrons.
Okay. Yeah. I like to think about it this way. Magnesium plus 2 must have more protons, so hence I must have lost electrons.
So
Oxidation is losing.
are we picking up the pen on this one?
We are picking up the pen.
Okay, I'll get that one.
Yep.
Okay. So we know magnesium is the piece getting oxidized. So we're going to make sure we keep everything on the right side of the arrows, right? Mg0 is on the left-hand side up top. Mg plus 2 is on the right-hand side up top. So we need to make sure that piece is set. And then how many total electrons? 2.
2 moles of electrons.
2, which is good.
Yes.
Okay, so next, if Mg0 is oxidation, then I think it's pretty safe to say Cu plus 2 then is reduction.
Yep.
And if I go from 2 more protons and electrons to having even number, I must have actually gained electrons. That's the way I like to think about it. Plus 2 is more protons. Protons are king. Remember that, guys? I
Yep.
used to say that 100,000 times. Protons are king. Two electrons are gained. They're on the reactant side, and there you have it.
And so when you combine these two oxidation and reduction half reactions, you get the reaction that we started with, which is written for us underneath the electrochemical cell.
And the reason why the electrons aren't there is because they're the same on the product and the reactant side, so they technically cancel out.
It's the same exact 2 moles of electrons that the magnesium loses that the copper soaks up. So you don't really have to show them in the balanced equation because they kind of drop out of the equation.
Right, but when I see them in the half reaction, it helps me understand which one's oxidation and which one's reduction.
Exactly.
So that's fabulous. We got half reactions, and we just broke down an electrochemical cell thoroughly.
Mhm.
All the pieces, right?
Yeah, and there it is. So what your little piece of inquiry is as follows. What would changing the more active metal do to the number of volts and current that a cell produces? Can you get a more powerful battery by changing the anode
Ooh, that would be fun.
to be a different metal other than magnesium? And
Yeah.
what would it happen
Yeah.
if you change that magnesium to, I don't know, aluminum or any other metal
Or zinc.
that's
or,
more active than copper on your activity series?
Yeah.
What would it do to the amount of electricity that the battery produces?
Right. Good. And the other thing I'm thinking when I see this particular picture is, what parts of this picture let me know it's an electrochemical cell and not an electrolytic cell?
Which is going to be our last lecture on the last type of.
So remember, just a quick recap, the important pieces here is there is a voltmeter
Yep.
or a resistor of some sort. And a resistor, that's a physics term, but it's a light bulb or anything we're powering.
calculator, a battery, a machine, a
Anything-
device that runs on electricity.
Yeah, anything that's not a battery, basically.
Mhm.
And then there's a salt bridge.
Yep.
Key. Only in voltaic cells you're going to see a salt bridge. And then you have your 2 separate reactions, your 2 separate electrolytes.
And the key questions that they always throw at us, and we'll do this in practice, is when the switch is closed, which direction will the electrons flow?
Right.
They're going to flow from the anode to the cathode
Right.
through the wire. So
And so you need
you
to be able
don't
to
want to just be like left to right, right to left. You should always say from the anode to the cathode.
Right,
And if-
or from magnesium to
To
copper. And you know that because magnesium is more reactive than copper using table J from last video.
Mhm.
And guess what?
Yeah.
Go ahead and say it.
That's all, folks. Thanks for watching. Where's my clicker? I can't find my clicker. There it is. Stop it.